Hello and welcome to another Zozin session. How about that? So today is Tuesday, and that means today, according to the schedule, we are working on our own programming language built on top of our own stack-based virtual machine. You can find the source code of this entire thing in the description, and yeah, let's just jump into it. So I plan to work on row pointers today. Because our language does need row pointers, and I'm not even sure if we have an issue for that. Right. Does not support pointers. Yeah, we will need to have them at some point because we want to be able to have some sort of an access to the memory. Right. We can already define global variables, but to be Turing complete, we need to be able to go left and right in the memory, like in, Turing tape or something like that. So, and once we have pointers, we'll be able to implement something more or less Turing complete-ish, like a rule 110 or for instance, Game of Life. We'll see how it goes. So yeah, let's just get started, I suppose. So it's sort of like a last piece that is missing in our language that will make our language useful for at least something. We're gonna implement pointers in a very, simple way and also in a very unsafe way, just to get things going. And once we have them, we will create separate issues for improving this entire stuff. All right, so let me see. We're gonna create and branch 128 because that's the issue number, right? So, and let me see what we've got. I'm gonna rebuild. I don't remember if I actually fetched the latest changes. I don't quite remember. Maybe I should have checked it first. So it's taking some time. Oh yeah, we have some sort of like global outage of web services or something. That's maybe why it is a little bit slower, but I don't know. Okay. So yeah, so we have the latest changes right now. Okay, cool. Let me try to rebuild the build tool just in case. No build.c. Okay, and then it's gonna be no build test. And all right, and so now I need to go to my branch and actually quickly forward it into the master, right? So everything seems to be forwarded into the master. So the first thing I want to do, I want to introduce the type for the pointer, right? Usually in the majority of the languages that have pointers, pointer is a generic type in the sense that it's usually parameterized by another type, the type it points to, right? In C, it is usually something like this, right? Right, you not only have the pointer type, but you also have a parameter of a pointer. And of course in Rust you have references, and references also have the type they reference to. So in our case, to just get things going, we're gonna go with a very simple solution. We're gonna have only a type. Which is called PTR. Right, and that type is basically going to be an equivalent of void star, right? So we're not going to have any syntactic sugar for referencing and dereferencing the pointers, right? So we're going to just introduce hard-coded functions for I don't know, reading specific types. So I want to be able to read, I64, right? Read I64. I'm going to provide the pointer, and this entire thing will compile down to dereferencing this pointer and reading I64. Again, this is not going to be the final syntax. This is not going to be the final way. It's just to simplify the amount of work I have to do right now, right? Because we just need to implement the pointers and ability to read and write to the memory in arbitrary places just to have something at least useful. And once we have that, we can start improving these things, piling up syntactic sugar on top of that, and so on and so forth. Because all of that is bike shedding, and getting into the bike shedding early on without having anything working is kind of a waste of time. All right. So I'm really sad that I have to explain this kind of things, but yeah, a lot of people just don't understand that first you need to get things going, and then you can start improving things, because it's kind of hard to improve something that doesn't exist, right? First, you need to have something that does in fact exist, and then you can start improving it. That's why these pointers that we implement in here are going to be pretty lame, and it is what it is, but they're going to be working. They're going to be working, and you will be able to do something useful with them. All right. So it's interesting is that maybe we're going to actually have something like, maybe it shouldn't be a read because it makes it feel like you're reading from the standard input or something. It could be something like deref, right? Deref. And you can provide the pointer, but maybe on top of that you will be able to provide the type, right? So, and that's going to be the thing that you can do. Right. So the reason why I'm going to go with this kind of syntax is because right now I won't need to even modify the existing parser to actually support that. Right. I just need to go into the compiler and just hard code this function, and there we go. So I don't need to do anything at all. That's the beauty of it. So we can have a ref, deref, and how can we set a value into the pointer? Right, so maybe it's gonna call something like store, and you'll have to provide the type, the pointer, and the value that you want to store in there, like something like 69. But maybe the pointer should actually go first here. Yeah, I think it does make sense. By the way, as far as I know, in WebAssembly, these kind of operations are called load and store, right? So you're loading a value from a particular pointer, and then you storing a value to a particular pointer. So, all right, that's actually pretty good. It's actually pretty good. So that's the way to go. All right, let's introduce first the type PTR and see how it goes. By the way, in the future, here's a couple of my thoughts. What's going to be in the future? Pointer has to be a generic type. That means it has to be parameterized by another type. So in languages like Haskell and stuff like that, types like generic types that are parameterized by other types are basically functions that accept one type and return another one. So because of that, maybe we're going to go the same route. Maybe pointer is going to become a compile time function that accepts a type and returns you a new type, the pointer to that type. So yeah, and maybe pointers to a particular types are going to look like this. It's going to be PTR of that type. So, and by the way, maybe because of this, like referencing a pointer, if you want to take a pointer to I, you're going to be doing it like this. Right, so essentially, you're going to have a compile time function, PTR, that accepts the type, and a runtime function, PTR, that accepts an actual variable. Right, so, and because of that, the syntax is going to be more or less consistent, but we're not going to implement it right now, so it's like for the future. For now, we're going to just have void star, right? Whether we're going to have like this kind of operation on variables, I'm not sure, but yeah, we're going to definitely have store and load. And store and load also going to have a better syntax in the future. All right, so let's go ahead and implement all of that. So I'm going to go to the library, and I think we have types somewhere in a parser. So it's called bang type. There we go. So we already have void, i64, boolean, and let's introduce yet another type, which is going to be called PTR. And let's try to recompile the entire thing and follow the compilation errors, because that will trigger some compilation errors. All right, so what we got? We need to come up with the name for this type. So obviously it's going to be called PTR. And now we already have 4 types in here. All right, and what's going to be the size of the pointer? I suppose since it's a 64-bit machine, it's going to be 8 bytes. So, by the way, all of these things can be compressed like this, and I can just add bank type PTR, right? So I'm just adding that. All right, is that it? So apparently that is it. So that means I should be able already use pointers in my examples, so this thing should already compile. And let me actually try that. Examples run while bang, and it already compiled, believe it or not. And if I try to assign p, like I to p, it should fail. Hopefully, it didn't fail. Why didn't you fail? We already found a bug. Apparently assignment doesn't even check what the hell are you trying to assign in here. And also surprisingly, when we're trying to compile this down to something, it also doesn't fail. Did I really recompile everything correctly? This is actually kind of sus. Why does it just work like this? I don't quite understand. Yeah, we don't know how to compile type pointer. Why the hell it is just working? What is... I feel like I screwed up yet again. Okay, so let's actually go to the compiler. Let's go to the compiler and see. So we have a variable assignment, right? So it's going to be var assign into boson, and what we're essentially doing, we're just compiling the expression. Yeah, we don't even check the type of a variable we're assigning. Oh my god. Unbelievable. Unbelievable. We check that the variable does in fact exist, right? We check that it does in fact exist, but we don't even check if the compiled expression is even assignable in any way, shape, or form. So yeah. So we compile this thing. Now what we can do in here is compiled expression, right? So here is the compiled expression, and inside of the compiled expression we should be able to just check what's the type of this expression, right? So if the expression type is not equal to the type of the variable, right, we can throw an error saying something like std error bang log fmt, right? It's gonna be error cannot assign type expression of type this to a variable of type this, right? So, and now we need to assign the location. So location of what we need to take, in fact. So we need to take the location of an expression, but we don't really have locations of expressions, unfortunately. Oh boy, oh boy, oh boy. So we're gonna use the location of the variable, right? So does the global variable even have a location? Yes, it does in fact have it. So I can do var log. Okay. So x cannot assign expression of type. So that means we need to use bank type name, expression type, bang type name, not expression type but variable type. There we go. So we're trying to assign the type, the expression of this type to the variable of this type, and after that of course we want to exit with 1, right, because we can't do that. All right, so if I try to recompile this entire thing, and we'll see what's going to happen. So now if I try to run it, okay, cannot assign expression of type. So the location was not the location of a variable assignment, it was the location of a variable definition. So you know what, I think I need to go to the compiler and actually rename this location to the def location, because I think this is already like second or third time I'm actually, you know, stumble upon that. Like I think it's a location of the variable, but it's actually the definition location. To be fair, maybe the global var, if you look at these three things in here, they're precisely the definition of the variable, right? So where's the parser? Bang var def. Yeah, there we go. The var definition consists of the location, name, and the type, right? If you just organize things like that, actually like this. So we have a location, name, and type. Right, and all of them are coming from the var definition. So maybe what I should do in here, I just have to replace this entire thing with the definition, bang var definition, and it's gonna be something like that. There we go. So this is basically a compiled variable. It's like compiled procedure but compiled variable, right? So that's actually pretty cool. But I still want to call it global variable because maybe variables on the stack are going to have like a slightly different definition, but they also going to have like an address or something like that. But yeah, maybe I should actually call it compiled var instead, right? And in here we're going to have compiled vars, and we're still going to call them global vars, right? Because we don't have any scope system yet. So similarly, I think we can do the following thing: compiled procedure. Well, it will be, if I try to refactor compiled procedure the same way I refactor compiled var, it's going to be too much of a rabbit hole, right? Because it will basically generate two parallel compilation error trails, which I'll have to follow simultaneously, and it's just going to be too much to handle. So I'm going to leave it like that, and I'm going to make it to do store bang proc definition in compiled proc the same way we do it for compiled var. There we go. So, and let's just follow this compilation error trail, and then we'll go back and start this one. All right, so there we go. I need to recompile everything one more time. So now I think what I can do is basically rename bank global var to compiled var. Super quick. So it's going to be that. Well, it was only one instance, which is not that big of a deal. Okay, so here's another instance. There's more of them in here. Anything else we need to do? Okay, so here's the thing. Var type is not var type anymore. It has to be var def type. How many of these things we'll have to do in here? So global variable, definition name. Maybe I can do the following thing, because I usually call them var, so it should be relatively easy to just replace var type with var def type. Yeah, there we go. There was only two instances of this stuff. Okay. So let's query replace var def lock. Yeah, and you can clearly see that it's a definition from the location for the definition. Okay, and this is where we're creating compiled var. So as you can see, we are assigning these things from the definition. Right, we're just assigning these things from the definition, and now I don't have to do that anymore. I can just do new var definition, and I can just remove this entire thing. There we go. So yeah, that was the right decision. I think that was definitely a right decision. Cool. All right, so it would make sense to actually compile this entire stuff. So I'm gonna commit this entire stuff, not compile. So this is where we edit the pointers. I don't want to actually smash together like adding pointers and refactoring bang global var. So I'm gonna be super careful in here. So all of that is about these kind of things. This is a pointer situation, and I think that is basically it. So we also added the type check. So maybe I'm gonna actually include that type check in here, and that's pretty much it. Okay, so this is gonna be the first commit. Rename bang global var into compiled var. Also, make it store the entire bang var def for future references during the compilation. There we go, and I'm gonna push that right into the repo. Okay. So let me see. I'm gonna go back to the compiler, and I think I want to refactor compiled procedure in a similar way. Yet again, it's gonna be basically bang proc definition plus the address, the instruction address where the procedure starts. You can see how similar compiled var and compiled procedures are. They're just their definitions plus the address where they're located. But for the compiled variable, it's a memory address, right? Because the variable usually is located in the memory. variable usually located in the memory, and compile procedure usually located in the program memory, so that's why it's an instruction address. So yeah, I think, like, I like that there is a symmetry between variables and procedures. I don't know why. It's kind of cool. I think I'm weird, so it shouldn't be that important, but I kind of like that there is a symmetry between them. It's just like, yeah, it's just pretty much the same thing. One is data, another one is code, and that's why they're located in different regions of memory or something. I don't know. All right. So proc definition, it should start with def. All right, another one. This is the def. And this is an absolutely similar situation. Look. Absolutely similar situation. Proc, address, location. All right, so that means I can do something like proc definition, proc def, and I can just remove this entire thing. Yep. All right, and it worked. Apparently it worked. Can I run this example? Okay, example is not runnable. Yeah, an example is not runnable because I'm just reporting incorrect location. Before I fix the location, let's actually commit whatever we have already. So here we have this refactoring. We have that. And there we go. 428 refactor, compiled proc. Make it store the bang proc definition for future references during the compilation of our nation. Okay, cool. So now, when we're reporting that you're trying to assign incorrect type to a variable, we have to take the location of the assignment, not the location of the variable definition. This is quite important. So compile var assignment. Where is the assignment? I cannot find it. Assign. Yeah. So, and now it is super easy to not confuse it, because you can clearly see that you're trying to get the location of a variable definition, not the variable assignment. So what you have to do now, you have to do var assign, and there you go, you're taking the location of a variable assignment instead of the variable definition. So, and that's precisely what you needed to do. So refactoring made it a little bit more clear. Okay, go. So if I run it, as you can see, it complains about this thing, but of course I forgot to put a new line in here. Right, classic. Okay, so if I run this entire thing, So as you can see, it says that it cannot assign expression of a type i64 to a variable of a type pointer. So, I mean, as I already said, I want to be able to do this kind of stuff. Right, so basically it should be able to take a variable of like any type and return a pointer. And I feel like it's not that hard to implement. It's actually not that hard to implement. Right, let me try to do that. A known function ptr. Let's actually make it known. Why not? So here's where we hard-coded all of the functions, right? So, and if the function that you're trying to compile is called something like ptr, right? We're going to compile it in a particular fashion, right? So first of all, we need to check the arity of the function. The arity is going to be equal to 1. So then what are we trying to do? We're trying to compile the expression of this variable. Do we need to compile the expression of this variable? I don't think so. We specifically want this thing to be variable read, right? We specifically want it to be variable read, otherwise we won't be able to take a pointer to this thing. So yeah, this is a special function. PTR is going to be a very special function right now, because usually functions first try to evaluate this expression, but this one should not evaluate it. It should try to look at it and see what it is. And if it's not a variable read, it should throw an error. So how can we even check for that? So we're going to take expression as fun call, right? And so we take the arguments and we take the value, right? So maybe it would make sense to actually take the expression, bang expression, and assign it like this, right? Is that a pointer? I don't think it's a pointer actually, so I'm going to keep it like that. So here's an argument. And what kinds of expressions can we have in here? So I'm going to go into the parser. So bang expression kind, right? And there we go. The one that we care about is a variable read, right? And if it's not a variable read, we should throw a compilation error. Okay, so if arg kind is not equal bang expression kind variable read, we're throwing an error. Bang log fnt error cannot take a pointer of... Is it even possible to convert this thing to some sort of a name? It should be possible. Cannot take a pointer. Okay. Expected... I don't even know. If we're gonna have a special name for this kind of thing, it should be called variable read. Yeah. Expected variable, but got something else, right? But got something else. Bang log fmt, and it's actually arg. And what we're gonna use in here, I think we have to do expr as fun call, and we're gonna use the location of this entire thing. Right, we need to have something like bang expr kind name, so I can take the arg kind and print it in here. And then I'm gonna do exit 1. Right, is it gonna work now? So also this implementation is not finished. I should not forget to put some sort of to-do in here, not finished. Right, so in case I forget to finish implementation, and let's try to compile this entire thing. So we don't have such function. Okay, let's quickly create it, I suppose. So we're gonna go to the parser, and we need a function in here, right? So bang expr kind name. So it's gonna be something like this. So we're gonna accept bang expression kind, and we're gonna return the name. We're going to return the name. Okay, let's go to the parser. Let's put it here, and let's switch upon different kinds of expressions. So, and what kinds of expressions we can have in here? Let's find out. Let's find out. Query replace this thing with that, and let's go here, and then I'm gonna do a case in here, boom, and also we're gonna have a default case. So count and default will lead into the unreachable situation, right? Something like this. Bang expr kind name unreachable, reach the unreachable. Okay, so and for the rest of them, let's actually return their names. Something like return string literal. So these names are needed for error messages, right? So we want to be able to just like embed them into error messages. Expected string literal, but for instance got boolean literal, right? So there we go. Integer literal. Function call. Variable read, right? This is a variable read, and binary operation, binary operator, right? Binary operator. There we go. So this is basically what we expect in here, and we should be able to use it now. variable read. Variable read is not particularly a good name for this thing, but okay, maybe it's fine. So, and if now if I try to do this kind of thing, yeah, this thing is not finished, but it didn't fail either. It didn't fail here either. So if I take a look at bang and I try to do something like 1 + 1, yeah, expected variable but got binary operator. Yeah, doesn't look like a good idea. I can also try to do something like write hello, right, which is also going to be incorrect thing, right. It doesn't look like a useful information. Like, it really doesn't look like a useful information, to be fair. So, yeah, we need to probably refactor the name. So expected variable, expected variable. Expected variable name as the argument of PTR function. So so hopefully maybe that is going to be a little bit more useful. Okay, I did a fucky wacky. I think I know what exactly I did. Expected variable, yeah, so I basically removed this thing and I forgot to remove this stuff. All right, so let me see. Okay, so if I try to run this entire expected variable name as the argument of PTR function. Okay, so and now if I try to put I in here, right, it fails in here. Okay, so what should it return? What should we return? It should return so result is a compiled expression, right? Result is a compiled expression. That means what we need to do, we need to query the variable, right? So compile global var. Get global var by name. There we go. So I need something like this. So we provide the context and we need to provide the names. So this one is going to be arg as var read name. There we go. And we got the variable. And most important thing, this variable stores, by the way, if you take a look, its memory address. And that's precisely what we want to compile this entire thing to. Right. This is what we want to compile it to. So that means we're going to be doing bosom push instruction, bosom inst push, and we take the variable and we use its address and we just push that address on the stack, right? We just push it on the stack. And after that, we say that the result type is going to be bang type PTR. There we go. So, and I think we managed to compile this entire stuff. I'm pretty sure we managed to compile. So variable incompatible type. Oh, it has to be Word U64. There we go. It has to be Word. And if I try to run this entire thing, it compiled in run perfectly. So now we'll be able to do this kind of stuff. You know what? I think I'm gonna create a separate example, PTR bang, right? Because I don't want to, you know, be concerned about this kind of stuff, and I don't want to actually ruin this example. This example just demonstrates how global variables and while loops work. So let's actually focus on something else. Yeah. So it's going to be a separate example. And here is the pointer. It's going to be something like that. And then I'm going to have this stuff. And the thing I want to do now, I just want to be able to assign a pointer of x to p, right? And that's it. And I just want to see what it's going to compile to. So let's try to run the pointer bang example. PTR, there we go. It didn't fail, and let's try to disassemble it. So what it compiled down to? Okay, so this is the entry point, and we actually go in here. So we push. That is very interesting. I suppose here we allocated 16 bytes. I'm pretty sure we allocated 16 bytes in here. So if I put the stuff in here, and for instance, for each of these things, right, I put a new line. Right, I put a new line, and then I just, yeah, it's 16 bytes. So first 8 bytes is for the variable x, and the another 16 bytes is for the pointer to that variable x. So we push 8, which is basically the address of the pointer, and then we push the value, which is the pointer itself, and we just write it there. All right, that makes sense to me. All right, that's actually pretty cool. I don't see anything special in there. What's interesting is that why pointer, expression of a type pointer, just compiles so easily, if you know what I mean. So I'm pretty sure like this shouldn't just easily compile, but it does. So variable read, so it has something to do with compiling variable read, and I'm not quite sure. Something bothers me. Okay, so compile variable read. Yeah, here's, we take a variable, we check if it exists, and we just push the address of the variable and we read it. Okay, so because we never actually check what the fuck we're reading. Right, so basically we treat any variable as i64 variable, which is not a particularly good idea. So that's why it never actually failed upon introducing the new type, right? Because it doesn't matter if it's a new type, we just treat them all the same way. So let's actually introduce something to distinguish them. So variable type, let's take a look. So, and let me try to compile this entire thing and make it fail, so I know what kind of types I have to dispatch upon. Alright, so it's not a variable type. I think it has to be variable definition, right? So it has to be variable definition. There we go, here are all the types. So can I now put something like this in here? Right, so can I now do the following thing? I'm gonna remove this thing, and I'm gonna grab this stuff, case, and I guess that's it. So, and another one is gonna be default in here. So compiling all of these things should result to just pushing their addresses and reading them, right? But if you're trying to compile void, for instance, it should fail. We can't compile a void. Or maybe you could. Maybe you could compile a void. So if you accidentally have a variable, void, that starts the void, that's kind of interesting. So first of all, you can't define a variable of type void. It's not a thing that you can do in the first place. So that means this thing is unreachable right now. And maybe that's precisely what I have to do in here, right? It is unreachable. Compile, well, maybe because of that, I also have to put this thing in here. Yeah, that makes sense. Since you never can define a variable of type void, you may never read a variable of type void because it will fail before you can even define it. That's why this kind of thing is straight up unreachable. So it's like a paradox. All right, assert fail compile var read into. Why can't you just autocomplete that for me, please? Compile. Okay. All right, so that makes sense. And this thing is simply unreachable. Right, So the reason why I did this thing is that in the future, if I add more types, I want this place to fail compilation so I can go back in here and just change things appropriately, because some of the types may have different sizes. So that means I will have to use different reads in here. And also assignment didn't fail, but I think I fixed the assignment, right? Assignment now cannot be done on the variables of different types, but yet again, assigning the variable is just like very much depends on the size of the variable. So this thing should also fail if we have like different sizes and whatnot. So we push the address, right? We push the address this entire thing. Push the address, then we compile the expression, and the expression compiles into something. Okay, I see. I think we do need to do that. So here is an address. I'm not quite sure. Like, I need to fix that. Otherwise this place is gonna bite me in the ass in the future. Right, it works right now quite fine because all of the types that we have are just 64-bit types. But if we start to have like more different types, like smaller types or bigger types because we introduced the structure, this thing will silently fail. This thing will straight up silently fail, and I will spend hours debugging and trying to find why the hell my new types don't work. So I need to put something in there, but I'm not quite sure what I have to put in there. So let's make a small break. I'm gonna make a cup of tea, and then we'll come up with something to put in here. All right. So what's going on in here is basically we're assuming that we know how to compile expressions of these types. We should not assume any of this stuff, right? So we need to first switch upon the expression type, right? And depending on expression type, we're gonna actually write them differently. So right now, all of them are written the same way, but again, in the future, it may blow up. Right, so all of the useful type right now are 64-bit numbers, so you can just use this single instruction for all of them. But if we're gonna start having structures and stuff like that, this invariant is completely broken. So we need to prepare for this kind of situation. So the way we're gonna prepare for this kind of stuff is basically we're gonna dispatch upon all of the types. And as we add more types, this place will fail compiling, and we'll go there and we'll realize, oh, okay, we don't know how to write into this kind of type, and we'll have to do something about that. So that's how we usually develop things, right? So I prepare for the future. So I can clearly see that in the future, all of that is going to be absolutely broken if we don't put any measures, right? So I just don't want to debug that for too long. All right, so let's switch upon all of the types in here, or rather maybe, yeah, all of the types in fact. Okay, so this one is going to be that. Case, and a boom. And this one is going to be the default. Cool. So this thing is straight up unreachable, right? This thing is straight up unreachable. So let's put it like this. Assert false. And what's the name of the function? This is the name. Unreachable. There we go. So I'm not sure about void. I'm really not sure about void. Why is it assigned? Assert. Okay. Thank you very much. So for the I64 boolean and a pointer, we just do write 64, right? Because it's just a 64 number. Pretty easy. What do we do for the void? So if the expression we're trying to assign to is a void, that means we went past this condition. So for this condition to actually become false, the variable definition should become void. But you can't define a void variable. So hence, this thing is unreachable, right? Basically, assigning expression of a type void to a variable void is unreachable, right? Because, yeah, you can't define such a variable, so this condition will never let you pass, right? So that makes sense to me, I suppose. Okay, hopefully now it's future-proof, more or less. More or less future-proof. So let me try to debug on this example. It's doing things, it's doing stuff, and I'm more or less happy. Right, more or less happy. So I was expecting these things to fail compiling. Right, as a matter of fact, can I try to remove pointer and just see that it will fail compiling in all of these places? Because it's quite important for the future, yet again. So where's the PTR? Okay, I'm gonna comment this thing out and let's see what's gonna happen. Right, what places is it going to fail? So it is failing in here, but I mean, this is expectable. Okay, it is failing in variable read. As you can see, it is failing here, right? So it reminds us that you need to basically be aware of how you read the variables of these kind of types, right? You need to be aware about this stuff. So we also compile this entire thing. Okay, so I can clearly see that it will remind us about all of these places. So let's actually go back. So static assert is going to be 4. All right, I just want to be extra cautious about this kind of stuff. Okay, all right, so let's do a committee for this stuff. So also maybe we don't even need this function anymore because I don't think I'm using it anywhere. Might as well just completely remove it, right? I don't think it's a particularly useful function. Right, so in the parser we edit that, in the compiler we edit all of that. Let me double check if this entire stuff compiles. Compilation of our nation. Sorry, I can't stop saying stupid stuff. Same 5 lines, by the way. Introduce type PTR. All right, let's push that right into the repo. So we have a type PTR. So the next thing we want to be able to do, we want to be able to read and write the pointers, right? So we need to introduce these load and store functions. So how are we going to do that? PTR. So we have a pointer to X. So what I want to try to do, I don't know, first of all, I want to assign this thing to like 69. We don't have a way to print them, unfortunately. We don't have a way to print them. So I have no idea how to basically even test that except looking at the source code. Right, we literally don't have any way to do that. We can only print strings, but I don't know. So we're assigning this entire thing, and what I want to be able to do, I want to be able to load P as I64, right? I want to be able to load P as I64. We might as well, okay, we might as well actually introduce some sort of like a dump U64 function that will, well, it will also need to be compiled into the code that prints everything appropriately. So it's not going to be an easy solution. Yeah, I guess we'll have to do that blindly. I guess we have to do that blindly. There's no other way. I don't see any other way. All right, so we want to have a load, right? A thing that will load I64 value from that specific pointer. So if I try to compile this entire example, right, something like this, it should say that this function does not exist. I don't know, maybe it would make sense to actually call it load PTR. It's a temporary function anyway, right? It's a temporary function anyway, doesn't matter. We're gonna have a special syntax for reference and dereference and pointers. It's just to get things going. All right, so we have a load PTR. and maybe you want to also do store ptr p. This one is going to be like +1, and you store it back. It is in fact inconvenient, I do realize that. That's why a lot of languages have a special syntaxes for reference and dereferenced pointers, so you don't have to do this kind of stuff. But yeah, so we're gonna try to compile this specific expression, right, and see how it goes. So it doesn't know anything about store ptr. Oh, and store ptr I think should also accept the type, right? Because we don't have a type associated with the pointer, we might as well actually provide this type in here and see how it goes. Okay, let's start with the simple expression. Yeah. Local ptr compiler. Let's go here. So what was that? It was ptr. There we go. So maybe it would make sense to actually separate these functions into something. You know. So result type. Nah. Let's actually like keep piling things on top. Else if sv equal expression as fun call name is equal to load ptr, right? We're loading ptr. What we need to do, we need to first check the arity of the function. So bang fun call expected arity is going to be expression as fun call, and how many arguments we expect in here? We expect specifically 2 arguments. There we go. So then we need to check the types of all of these arguments. The first argument is supposed to be just a pointer, so, and also this is an expression. This is a runtime expression that we have to evaluate at some point. But this one is a type, right? It's a type that we're trying to read. So that means we need to do something with this type at compile time. We need to do something with this type at compile time. So I'm just thinking what's going to be like easier thing to do. I think I'm going to actually swap these things around. So the first you're going to provide the type, and then you're going to provide the rest of the stuff. So bang expr type argument, right? So expr as fun call args. So maybe it would make sense to actually have something like fun call args, right? So here's args, and I'm assigning the arguments like this. There we go. So this is going to be args value, right? Args value. So this is the first arguments. And what do we expect in here? Right, this entire thing should compile down to a variable read. Right, because it's a name, so this entire thing will assume that it's a variable read. But in fact, it's a type. So we don't have a special AST nodes for types, unfortunately. So that means it's going to be a little bit of a hack. So if type arg kind, I think, bang expression. So pass something like this, bang expression as, it has to be a variable read. Bang expression kind var read. There we go. Here's the var read. If this thing is not a variable read, right? If it's not a variable read, we have to throw an exception, right? We have to throw an exception. On top of that, we need to validate that it's a correct type, right? We need to validate that it's a correct type. Yeah, that's a lot of work, but I mean, we just need to do that. We just need to do that. Fprintf std error bang lock fmt error expected type name, right? Expected type name. Bang log arg, and we need to extract the location of the function call, right? So then it's going to be exit1. There we go. Extract the location of a function call. So after that, we need to take the type arg as var read, and we need to take a name of it, right? And we need to try to parse this name as a type. So as far as I know, the parser has a way to parse it as a type. Parse var read bang type. Yeah, parse bang type, but parse bang type accepts the lexa, right? It accepts the lexa. Yeah. And what we do in here, we actually iterate through all of the types in here, and we see if it's equal to a particular type, and then we return all of that. It would be actually better to have a separate function for that. That is something like bang type, or rather, yeah, bang type. Bang type by name, right? And you just provide the string view name, and this function essentially does that. Right, basically does that, or it says that it's an invalid type. Though, I think because of that, it should return maybe a boolean, right? It's going to be bang type, and it's going to return it like this. So it's going to be true. So out type, if out type is defined, it's going to be out type equal type, and then this thing is going to be returned false. There we go. This is basically what we want to have in here. So when it's needed, so it can be reused outside of the parser for these kind of things. So yeah, basically we're trying to do the parser job of figuring out whether it's a type or not. So there's some friction in here, meaning that the system is not really designed for what we're trying to do right now, but we'll figure out a little bit later. Okay, so now I need to call this function in here, right? I'll need to call it in here. So the name is going to be available in the token text. So here's token text, and the type, the output type, is going to be somewhere here. Bang type result. I need to assign it to something, but let's assign it to 0. So this is going to be a result, right? If this thing is working, right? Let me remove it. So maybe this is going to be like type. Then I'm going to just return the type. There we go. Otherwise, we're going to crash. Cool. So after that, we're going to do bang type, and bang type by name, and I'm going to provide the type. If this thing failed, right? If this thing failed, we need to actually say that this thing does not denote a proper type. Okay, so fprintf std error bang log fmt error svfmt is not a valid type, right? Is not a valid type, and what we're going to provide in here. So this is the type argument as variable read name. SVArg. We also need to provide the location. I completely forgot about the location. And what's going to be the location? I think it's going to be location of the function call. Yeah, it's the easiest thing to find in here. All right, and then it's just going to be exit. Okay, so we have type argument, and then we extracted the type out of it. Cool. And so what's going to be the next thing? PTR bang. We extracted the type, and next one is going to be actually the pointer, right? Next thing has to be actually the pointer. So what I need to do now? I kind of want to wrap this entire thing into this, right? So now here we're figuring out the type of this entire thing, and we don't care about this thing and all of the other stuff. But we also should not forget to advance args to the next one, right? We should not forget to advance args to the next one. And the next one is going to be something else, right? So this is the second argument. We take the bang expression, it's going to be ptr arg, arg's value. There we go. So, and after that, we need to try to compile this into a pointer that we can push on top of the stack, right? Push on top of the stack. All right, so compiler, compile expr, bang expr, yeah. So we provide the bang, provide the bosom, we provide the pointer arg, and here we have a compiled pointer arg, right? So here's the compiled pointer arg. So if compiled pointer arg type is not equal bang type ptr, we're gonna say that I'm sorry, expected pointer but got something else, right? fprintf std error, bang log fmt, expected s but got s. All right, so bang log arg, so this one also has to be allocation, right? Has to be allocation. So what we expected here, bang type name, right? Bang type name, bang type ptr, and then, but we got actually compiled ptr arg type, and then we're gonna exit with 1. There we go. We got that. So we compiled everything appropriately. So maybe because of that, I want to actually move the definition of this entire thing somewhere here, right? I'm going to zero initialize this entire stuff, and then we just basically assign it in here. So here, first we're figuring out the first argument, which is the type, and then we're figuring out the second argument, which is the pointer, right? So maybe it should be actually pointer expression, right? So I don't know. Yeah, I guess it's fine. Compile pointer arg. All right, cool. So after that, we need to switch upon the type, right? The type argument. And let's see what's gonna happen. So we can only load I64 boolean and pointer void is not a thing that you can load, right? It should be unreachable. If you're trying to load, well, I mean, technically you can load, yeah, because you can just put void in there, right? Since you can just put the void in there, that means it's a valid thing that you can get from the user. So it means on a void, we'll have to say, cannot read pointer to void, like it's a meaningless separation. And you shouldn't do that anyway. So, okay, let's take a look. It's going to be parser, type, bang, type. Okay, so here are all of the things that you can do, that you can have in here, right? So it's going to be that, then it's going to be case, and then that's fine. Okay, then we're going to have default. Okay, I'm going to bring this all down. Cool. So I already compiled the pointer argument, so that means it should already have that pointer on the stack, right? So, and that means the next thing I need to do is read something, right? So I just need to read this kind of stuff. Oh man, okay, so I64 should use a read I64. A boolean and pointer should probably use a read U64. Okay, so it's going to be bosom, push instruction, bosom, instruction read 64i, okay. These two have to use this thing, and of course for both of this stuff, word U64 0, because they don't have any operands. Here we have a break. This one should be unreachable. Assert false. I should probably put something here as unreachable. 177. Okay. And unreachable. Exit 1. Okay, in case of a void, we need to say something to the user because the user may straight up actually put a void in there. fprintf std error bang log arg, right? It's a bang log arg. Error could not cannot read cannot read void types. Okay, cannot maybe, yeah, read void types. Maybe load. Okay, so bang. This one has to be fmt arg, and it's gonna be again the location. So this is gonna be something like this: the location 13, and the type is gonna be bang type name bang type void, right? Bang type void, and this is one going to be exit 1. There we go. Bang type void. All right, that took some time, but I think we managed to implement load pointer function, at least outline what needs to work. I don't know if this compiles or not, right? I was just like dumping my thoughts into the code. So yeah, essentially we just need to compile this pointer and we just need to read into this stuff. And as we read, by the way, we need to assign the result type, and we do know precisely what's going to be the result type. The result type is going to be actually the type that we got from here. So we already kind of have generic functions in here, right? So the final result of this function call is whatever you put in here. Right, so yeah, you have a generic function and you can pass the type as an argument in here, right? So it kind of is a generic function in some sense. So all right, maybe we at some point we're gonna take this entire like code and extract into more generic mechanisms so the user can actually have their own functions that accept like types. Right, so it's going to be t type, and then you can have a variable of that specific type, and there you go. Here is your generic function, right? And you can maybe then you can say that then it returns that type in here. Right, maybe I want to make it actually capital, I don't know, and you can do things like that. I64 and then 69, and yeah, we'll see how it goes. We'll see how it goes. But we have a hard-coded generic function that can read from the pointers, because pointers right now cannot have associated type with them. All right, so let's see if it compiles. It probably does not compile, but we're going to go through the compilation errors and we're going to fix everything. Okay, so what do we got in here? So build type by name, implicit declaration. This is because I implemented this function, but I didn't declare it as public function. So let me put it somewhere here. So it's available to everyone. Bank type. Do we even have something about the bank type? Bank type. Here you go. So we have two opposite functions, like bank type, which takes a type and converts it to a name, and then we have the one that takes the name and converts it to a type. Okay. So bank type name and bank type by name. You can use both of them if you want to. All right, so what do we have in here? We have a token SV from sister, token undeclared. Okay, so that means I quickly have to replace token.text with the name in here. Okay, there's only one instance of that. That's totally fine. Is there anything else? Okay, it compiles almost first try. Would you look at that? I'm sorry. All right, so I wonder if our final example will compile. We'll see. We'll see. We'll see. So, where is my example in here? The example, yeah, basically assigns this variable, takes a pointer, and loads the pointer. Let's try to just compile this example. This is not how we do that. You have to do that from a different place. It compiled. Would you look at that? It in fact compiled. All right, this one is interesting. It actually does double read in here, and the question is why. Oh yeah, I can see that, I suppose, because it returns. Yeah, this thing returns expression. So the pointer itself is located in the memory. So first you need to extract the pointer from the memory. This is where the first read comes from. And then you need to read whatever is located by. Yeah, this is why you have double reads. So the first read reads the pointer from the memory, and then you read it again. So yeah, that makes sense. And since this is an expression that returns something, we need to drop the result, and then we can return back into the entry point and hold the machine. All right, so let's see if this entire thing can even run successfully. One more time. It ran successfully, so it didn't stack overflow or stack underflow. It just like ran successfully. All right, so it didn't try to access like incorrect memory or anything like that. This just ran flawlessly, and yeah, I'm super happy about that actually. Okay, can we try to implement something else now? For instance, store PTR. So we're gonna accept the type, yet again, then the pointer, and we can try to store something in there, right? Something like this, So this one is very similar to load PTR, except it takes the third parameter now, right? It takes the third parameter. We're gonna reuse a lot of code from the load PTR. So I want you to actually extract something from there. Let me find the compiler. So one of the things that I want to reuse, in fact, is this thing, right? I want to be able to quite easily just take an argument and treat it as the type, right? So let me see. So essentially, I want a function that can return me just bang type, but what it accepts is bang expression, right? It accepts bang expression, but returns me a bang type. So how can we call this thing? Because again, the reason why we need this function is because we don't have a separate AST node for types. Right, we don't have a separate AST node for types. And this is because like the parser is not aware of the context, right? It doesn't know that some of the things can be compile time values, some of them may not be compile time values. Maybe because of that, we want to have some sort of like syntactical distinction between compile time values or not, right? Somethings, just prefix this thing with something. But I don't think it's actually needed in here. Okay, so we can do something like reinterpret expression as type, right? Reinterpret expression as type, if possible. Okay. So let me see. So I'm gonna take this entire thing in here and just copy paste it in here. So here's an expression. So maybe because of that I want to call it type arg. So that will let me do something like this. So the only problem I see in here is that now we need to know the location. But we just don't have a location associated with a bang expression, unfortunately. But maybe we should actually add that. Maybe that's something that needs to be added. So I want to be able to just do something like, you know, just a second. Yeah, expression log, right? Just report the location. So we don't need to do this thing in here, that's for sure. And then, so this is the result type, bank type, initially 0, and then I just return this type that was successfully parsed. Type arg as var read. So only the var read can be reinterpreted as the type. Otherwise, you won't be able to do that. Expected type name. So let's go to the parser. Bang expression. Where is the bang expression? Yes, so we have a kind as, and now we need to have bang exper lock, right? I want to have a location in here. So, but now, as we need to find all of the places where we construct the bang expression. I think we only construct them in here. So bang exper, right? So here are all of the places where we construct, and that's a lot of places, not gonna lie. Right, so it's basically parse primary exper, right? It's basically parse primary exper. Do we even know any locations in here? I think we do, right? So first we pick into the token of the expression, and depending on this kind of token, we're doing different things. Exper lock, token lock, right? Bang exper. I'm specifically searching for these things. All right. Another one. Another one. This one is rather interesting. So this is a parse bang expression. So this is about yeah. So this is gonna be talking. I think it's fine. All right. So cool. So let's try to recompile this entire thing and see where it fails. So bang exper lock. I think it's just called bang lock. Yeah. Reinterpret. So no previous prototype. Okay, so this one is quite an important function. It's quite an important function. Do we have anything else? Exper is undeclared because it's a type. Clear replace exper lock with the type arg lock because it's an expression anyway. Okay, so there's another one. So this thing is unused, as you can see. Cool. So in a load pointer, now instead of doing this kind of shit, what I want to do, in fact, is simply args value and then reinterpret expression as type, and I want to remove this entire shit. There we go. There we go, in fact. Nothing particularly special. So yeah. So after that I want to do args next. So as you can see, I just parsed the type, and now I need to parse the compiled thingy. Do I need anything special in here? I don't know, maybe. So I can try to do something like this. So this one is going to be pointer arg. So the actual arg is going to be args next value. So we take the first one, arg value, and then args next value, right? And maybe because of that, we don't need any of these things anymore, and then I just can flatten this kind of stuff out, right? So yeah. All right, so we check that we have two arguments in here, right? Then first argument is reinterpreted as the type. The second argument is compiled. Then we check, of course, that the type of a compiled thingy is pointer, and if it's not a pointer, it's like, you know, it failed. Type check. And then we're compiling everything in here. So that's precisely what I wanted to have in here. And now this kind of thing is reusable for store pointer. Right. And compiles. Almost first try. Unknown function store pointer. Okay, so that's fine. So let's introduce the store pointer in here. If sv equal expr as fun call name, and it's equal sv store pointer. I don't quite understand why I'm referring to such a long thing in here. I know for a fact that it's a fun call. Can I do something like bang fun call, and just reassign this entire thing to a fun call? Right, so I know that it's a fun call. There's no reason to like go expr as. Let's quickly replace expr as fun call with fun call. Not that one, but the rest of these things. I think that should make the entire code way shorter than it is right now. Yeah, because literally there's no reason to constantly like call to this thing. Yeah, so we have a fun call. You expect an arity. You also reassign fun call args. Yeah. It's almost like a Kotlin automatic conversion to the types. It kind of reminds me of that. Kotlin auto cast or something. Type checks and cast. Smart casts, I think. So there was a pretty good example. Maybe this one is also a good example. I don't know. All right. Yeah, okay. So for example, you have an object of some abstract type, right? Its type is object, as abstract as possible. You check at runtime whether it's in fact a string, and if you try to access this object inside of this branch, it is automatically casted to string. There's no reason to, you know, do that explicitly. So it kind of reminded me of this kind of situation. So we checked that the expression is fun call, right, and now we can refer to it as fun call. There's no reason to constantly cast it. There's no reason to constantly do expr as fun call. Let's just assign it once and just use it throughout the entire thing. I'm not a big fan of JVM languages, to be fair, because, well, I worked professionally with JVM languages and my life was absolutely miserable. So I burned by them really hard. But JVM aside, Kotlin has a lot of interesting ideas in terms of like constructions and type system and whatnot, which is quite cool. I wish it was not a JVM language. I wish it was not a JVM language. But Zozin, what about Kotlin native? Okay, so let me see. Bang fun call expect arity. So store PTR expects 3 arguments as far as I can tell, right? So here's the 3 arguments. Bang fun call arg, and then args fun call args. So the first argument, yet again, has to be reinterpreted as a type. So let's do something like this. Bang type reinterpret expression as type. So this is going to be the first one. The second one has to be a pointer, right? So compiled expression, pointer arg. And I wish I could maybe standardize this entire stuff. So essentially, okay, I want to do something like this for sure. I want to do something like this. Why not? But I don't want to type this condition all the time. Can I do something like expect expression to be type, right? And after that, I can say I want it to be bang type pointer, right? And I can wrap this entire condition in there. So yeah, expect compiled expr to be type. Yeah, and that way I can compress this entire thing as well. So this is the second argument, right? So, and then I want to have, so this one is interesting. So in a store, we have a pointer, and then a value. And usually when we do a write, first we have a pointer and then a value. I think first is the pointer. I don't quite remember. bm.c. So here's a bm.c and inst write anything, right? 8. So it's a memory address. So the first one is a memory address. So that means we can actually compile them in this specific order. Okay, so and then we can have another compiled expression here. So compiled value argument, right? Compiled value argument. And what are we doing here? We just compile bang expression into bosom. We do bang bosom, but this one is going to be args next value. I don't know what would be better, to be fair. Maybe it would be actually better to have something like bang fun call. So bang expression arg0, and this one is going to be arg's value. Then arg1, which is next value, and arg2 next value. And that way you can just do something like arg0, arg1, and then arg2, right? So something like this. So and then we compile this entire thing, and we can now type check it. We expect this entire thing to be the type of this type. This is actually quite interesting. So yet again, we're essentially having a generic function. So that's kind of cool. So basically, because of its genericity, right? If you provided this type in here, you only allowed to put I64 type in here, and this will be type checked, and this will be 100% type check. But the final result of this thing has to be void, I think. Yeah, that's kind of cool. Huh. I'm just learning how the generics work internally, right? I'm just learning how they work internally. So here we interpret it as a type, and then compile the first one, compile the second one, and we double checked that it's that type. And now we need to learn about how do you write different types, right? How do you write into different types? So if the type here is that, I guess we just need to do write 64, right? We just write 64, and we do that for all of the three types. Cannot store this kind of type, and the final result, result type, is going to be bang type void, if I understand correctly. So yeah, that's pretty much it. So maybe this kind of function is too long, but it is what it is, and it isn't what it isn't. I wish I could somehow, maybe I should use arrays instead of linked lists, but they're kind of difficult to parse if you don't have reallocation, and we don't have reallocation. All right, so let's try to compile this entire thing and see what needs to be fixed. So we'll need to create this fun. Yeah, expect compiled export to be type blah blah blah. Right, so here's that one, and so we're gonna accept compiled expression bang type expected type, right? Expected type, and this thing is going to return, I suppose, compiled expression, right? It's just gonna return the compiled expression, but maybe it shouldn't. Maybe it shouldn't. Maybe we're just gonna do it like that. And because of that, you will be forced to separate this entire thing. Yeah, I think it's a good idea. Look. Yeah, so you just do it like this, right? Here's your thing, and then you do expect compiled expression. So you take your compiled pointer argument, and you expect it to be of a type of bang type pointer, right? There we go. So you already simplified this entire thing. And then we're gonna use it like that, and then we say expect compiled export to be type. Yeah, this one is a compiled value arg, and you would expect it to be type. So compiled pointer arg is also a pretty long name. Let's actually call it pointer, and maybe there's no reason to call it arg. Let's just call it pointer, and this one is going to be just a value. There we go. So here are 3 arguments. So you have store ptr, you check the arity, and you extracted all of the arguments 0, 1 to 3. So you reinterpreted that one as a type, then you compile the pointer, you compile the value, and then you wrote the value into the pointer. So yeah, okay, that looks good. So this looks pretty readable. Everything is compressed. The complexity got compressed very nicely. So what we need to do in here, if expression type is not equal to expected type, right? It's not equal to expected type. I'm just thinking, can we actually do something like this? What if I accept like actual type and expected type? So this thing has nothing to do with compiled expert. So that means I can remove word compile expert from this function. What if we call it type check? That's it. So you have actual type and expected type. Type check. And because of that, you can just do actual type not equal expected type, right? And this one is going to be something like fprintf, std error, bang. We don't know the location of our nation. Okay, we know the location of our nation, so that means we still need to accept the expression. Okay. Okay, so we can do something like this. Compiled expr. So type check expr. Like, I don't like that this function has such a long name. All right. So if expr. By the way, does compile expr even have the location? Right, does it even have a location? It doesn't even have a location, it only has a type. But we do need the location. We do need the location. It's very, very important. Because otherwise I won't be able to properly type check. So the question is where we're going to put this stuff. When we are producing compiled expression. So maybe we can do something similar with compiled vars and compiled definitions. We can just have the definition of that expression. Yeah. So I don't know. We can just do bang expr. So it basically stores its AST, right? Why not? Why not? Yeah. So it stores its previous AST, but that means I have to go into the compiler, alright, and find all of the places where we do compiled expr, and something, maybe just expr. So where do we define that? I need to find it by a regular expression, compiled expr, then I ignore everything, and then I want to see something like 0. How many of such places do we have? Okay. Not that many, so which is fine, I guess. So we compile bang expression into bosom. Yeah. So it has an AST and then a value and then the type. So the result is this. So here's the expression kind. And maybe because of that, we want to do something like result AST, the original expression that we're assigning in here. Okay, so that should be fine. So now we have an expression, an AST available there for you. So let me see if it's going to compile now. Well, it's definitely not going to compile because I screwed up something in here. All right. This one has to be static. Okay, whatever. Let's continue developing. If expr type is not equal expected type, right? Expected type, we're going to do something like fprintf, std error, bang log fmt, error expected type this thing but got this thing. So the location bang loc arg expr ast log, right? Expr ast log is going to be that one, and expected type bang type name expected type name, but actual type was bang type name expression type, right? And then I can just do something like this. What else do we have in here? So yeah, it's called type check expression. Type check expression. There we go. Cool. And now I can go back to load PTR and get rid of this stuff as well. Right. So now I can just do type check expression. This one is going to compile PTR arg, and I expect it to be bang type PTR, and I can remove this clunky thing. Cool. Also, maybe it would make sense to get rid of the compiled PTR, just call this PTR. Why not? And also let's have bang expression arg0, arg's value, and then we're gonna have arg1 next arg0 arg1. There we go. So it's a little bit more readable. We compressed some of the concepts in here, and the functions that we came up with while doing all of that are going to be very useful for other places in the compiler. Hopefully, we'll see how it goes. You never know. You never know. Compiles, surprisingly. Why the fuck does it compile? I have no idea. So, let's try to compile this example. Right, so we implemented store PTR, and let's see what's going to happen. Let's see. So examples run PTR bang, and it just worked. And let's actually do debug them, and we do have reads and writes and stuff like that. And as you can see, we're actually like pushing. Okay, so I'm reading this thing. Looks all right actually. Did I set the type to the void at the end of the store PTR? Yes, I did. I wanted to check something. Right, so I assigned i64 in here. What if I put a boolean in here? Right, what if I try to store true, but I said that this is going to be 64? Let's see. Expected but got boot. Okay, this is actually fucking perfect. Yes, it fucking checks all of that. We have a generic function. What the fuck? Okay, so I forgot a new line in here, so it's not that big of a deal, but yeah, you can put like a type in here, and yeah, so you basically have a generic function. That's pretty cool. It's kind of interesting, not gonna lie. So let's actually run the tests. That's pretty poog. All right. So, and you can do the other thing, like if you put boolean in here, it will work, but if you do a boolean in 69, yeah, boolean but got i64. So they have to be synchronized, otherwise you won't be able to even do that. Right. And one of the things we can do in here, right, we can actually chain them together like this. Right, and it's compilable, as you can see, it's compilable. I can try to load boolean and save it as i64, and that won't work. Yeah, because this thing returned boolean, but here we expect i64. Yeah, that's actually pretty cool. So we can't really we could derive this information automatically if the pointer had an associated type with it, right? But it doesn't have the associated type with it, so that's why we have to pass the type to these functions for now. In the future, we're gonna have like, pointer is gonna be generic type, and you'll be able to do these kind of things. But for now, it's gonna be like that. Maybe I'm gonna even create a separate function specifically for that. Where is a bank type? Where is a bank type? To do there is no generic PTR type, right? Generic PTR type. Okay, so what useful things can we do with load PTR and store PTR? Well, we can now have some sort of like rudimentary arrays, right? So if we knew, okay, when we allocate global variables, right? So they are appended in the global memory. So the memory of the BM is sort of like a global array, right? Memory. It's a global array. If you allocate a variable x, we allocate a little bit of memory here, and there you go. This is where your variable x is located. You allocate another global variable like a pointer, and this is where it's going to be located. So we need to know where global variables end. I think we could expose some sort of implicit variable that stores the pointer after all of the global variables. And maybe we're gonna call such variable something like heap base, right? So we're gonna call it something like heap base. And knowing the heap base, we can implement a very simple linear allocator, right? So we would be able to just provide how much bytes you want to allocate, and this thing will return you the pointer and advance some sort of a global pointer of how much memory was allocated. Once we got that, we can dynamically now allocate buffers and arrays, and for instance, we can finally implement printing of the numbers, right? Because printing of the numbers, you usually just chop off the digits using like division and modulo, right? And you push them into the buffer, but then you have to reverse the buffer. So that means you need a little bit of memory to be able to do that, unless you're doing that recursively, but we cannot do it recursively because we don't have function arguments. But we'll need function arguments anyway at some point, so we'll see. But yeah, let's try to implement that. So let's try to implement the heap base. Before we're gonna go and implement the heap base, I think I want to do a committee and maybe even a small break. All right, there's no generic type, blah blah blah. Okay, so what we did in here, yeah, we straight up just introduced load pointer, store pointer, and load pointer, right? Nothing else. So this is basically what this commit is all about. Okay, it's going to be 428. Implement hard-coded load PTR and store PTR. And there we go, and I'm going to push that right into the repo. All right, let me make a small break. I'm going to make a cup of tea, and we're going to implement a simple like heap memory allocator, which is linear, and we'll be able to allocate something. Yeah. Okay, so here's the thing. So we want to be able to know where all of the variables end in the memory. So I decided to go with the following approach. Is that basically after we finished compilation, we're gonna check if the user defined a global variable called heap base, which is the pointer. And if they defined a heap base, we're gonna store the location of the end of the static memory there, so the user can use that pointer to allocate more memory and do some interesting things. Right, so let's see how we can do all of that. So where do we end the compilation? Let me find bang.c. This is not bang.c. Bang.c. So generate entry point. Oh yeah, okay. So what would be the best way to do? So we compile bang module into bosom. Then we generate entry point, and I want to have another thing in here. We can do something like bang generate heap base. I'm not even sure if it needs bosom per se, but maybe it does need bosom because we're going to be maybe initializing this variable with a particular value, right? We're gonna actually initialize it right in the memory. So maybe we're gonna also provide the name of the variable, so it's gonna be heap base. So this kind of stuff is gonna be customizable. All right, so we just need to implement this function that generates the heap base. Bang, let's go to bang compile. So, and this is where we generate an entry point. So we're gonna have a similar function bang, generate heap base, right? Bang, bang, bosom, string view, heap base var name, right? Heap base var name. Let's go to the compiler.c. Let's go to the compiler.c and implement this thing. So the first thing I want to do, I want to query the global variable, right? Global var. So something like global var by name. There we go. So we're going to provide bang and heap base var name. Okay, heap base var. If heap base var is not equal to null, we're gonna do all of this stuff. If it is equal to null, we're not gonna do anything. Right. So essentially, it's actually a pretty simple solution. The user may use heap base only if they define it. If they didn't define it, they cannot use this variable, so there's no need to even generate anything for this variable. You see what I'm talking about? Right, because they can't use it anyway. Right, I don't want to implicitly generate this variable. So the easiest way to do that is just like let the user define it themselves, and they can decide whether they want to use it or not. You know, zero cost abstractions. You don't pay for what you don't use. Zero cost abstractions. Yeah, hell yeah, brother. Cheers, by the way. But if it is defined, it must be of the type PTR. So, and this is probably something that we can check. So if heap base var, I think we need to take a look at the definition, but maybe compile var already contains its type. I think it's located in the definition. Yeah. So it's going to be type. And if it's not equal to bang type PTR, we're going to throw an error explaining the situation. Bang log fmt error. The svfmt variable is expected. The special variable is expected to have to be of type this, but it was defined as type this, and this is a problem, right? Because we expect a particular type from this variable. So the name of the variable is a heap base var name. This one is going to be svarg. We also need to put a location somewhere. I suppose it's going to be the location of the definition. Bang log arg, and it's going to be heap base var definition, right? So here is the definition and here is the location, right? Definition and location. And the type is going to be the following: bang type name, bang type PTR, right? And then bang type name, bang heap base var def type. There we go. Exit 1. All right, so we checked the types and warned the user if it's not of the right type. So the next thing we need to do, we need to save a value into that variable somehow. This one is going to be very interesting. So first of all, we need to figure out what is the heap base address. So this one is going to be something like memory address, heap base address, right? And it's basically the end of the memory, right? It's essentially the end of the memory. And if we take a look at the bm.h, so memory size, I suppose, right? Do we even keep track of how much we allocated? It has to be in bosom somewhere. Memory, yeah, I think it is a memory size, which is can grab the memory size and interpret it as the address. All right, should be relatively easy. Should be relatively easy. So bank compiler heap base address bosom memory size. There we go. We know a heap base address now. Now we need to store it into the variable, right? But we need to find the variable in the memory. So we need to do something like heap base var address, right? Then we need to take bosom memory and find where this entire thing located. And I think what we can do in here is essentially memcpy. So this is going to be the destination. The source is going to be heap base address, and what we're doing in here is just the size of heap base address. There we go. Heap base address. All right, that's pretty cool. That is it, actually. That is actually it. Do we need to do anything else? I don't think so. Yeah, so we're generating the heap base now. That's pretty pogue, not gonna lie. All right, so if I try to recompile the compiler, recompile the compiler. All right, and then if I try to run the example, compile example, everything seems to be fine. So here is a bunch of, oh, wait a second, I think it worked. Yeah, because all of them are not filled with zeros. There is an address somewhere here, which is 18 or some. My God, I think it worked straight up. PTR bang. Yeah, here it is. If I remove this entire thing, yeah, it's not available anymore, and the compiler doesn't even try to do anything. But if I define the address, here is the address, and it points like precisely there. That is goddamn cool. So what we can do with that now? That's actually pretty interesting. At least we know where things start. We can do different things. For instance, we can load U8 from the heap base. Right, and it's going to be a single character that you can work with. You can also store this thing like somewhere. You can store some characters in here, and you can access the next character by doing like +1 or +2, +3. But the problem is that this one is interesting. We don't have a pointer arithmetic, right? We just don't have the pointer arithmetic. So we need to be able to cast this kind of stuff. You know what? Maybe we can introduce something like cast PTR. Like this, so you can do pointer arithmetic, if you know what I'm talking about. Yeah, that will be actually kind of pogue. But on top of that, we also need to implement U8, right? So I want to be able to access individual bytes, because that will enable me taking a number and converting the number into a string, so that then I can print this entire thing. Yeah, we'll definitely need all of that, but that's a lot of things that we need to implement. First, we need to implement a new type, completely new type, with a different size, by the way, because before we worked only with the variables of the size 64 bits, this one is 8 bits. Then we need to implement pointer arithmetic, we need to implement cast, and so many things. All right, so will we have enough time to do that? I'm not sure, so I'm gonna give it a try. But yeah. So there's a lot of things that we need to implement just to be able to convert numbers to strings, and it's kind of interesting. Okay. 428 introduce heap base. I want to also check one thing. What if it's going to be I64? Will the compiler complain as expected? Yeah, okay, so, the special heap-based variable is expected to be of type pointer, but it was defined as type I64, and of course I forgot to put a new line in there, right, classic. But apart from that, I think it worked as expected. All right, so that's a pretty good mechanism of defining like special variables, right? So if you don't want to use this variable, you just don't define it and we don't complain about it. But if you define it, it's better be like of a special type. And then we can put this variable into the standard library, right? And the user of the language is just going to import this standard library without even thinking whether there is a heap base or there is no heap base. And it could be used for like memory allocations, dynamic memory allocations, and some other stuff. Okay, so what's going to be the next thing that we can implement? Let me try pointer arithmetic and see if it's going to work or not. So store, actually load ptr i64 p plus 1. What's going to happen if I try to do something like this? It's definitely not going to work. It's only supported for i64. All right, that's very interesting. What if I, swap them around? All right, so they all has to be equal to pointer and i64. So what if I just enable support for pointer? Only supported for all right, 56. Okay, compiled LHS not equal i64 is only supported for that. And this is only supported for that. P kind plus. Oh, P kind plus. Just thinking, we can quite easily probably do something like compile equal or, and this thing is not equal to a pointer, only supported for types and s, right? Bang type name, bang type pointer. Yeah. And well, I mean, it's a hack, right? But it will make things work for now, at least, hopefully, for type S and S. There we go. Let's see what we have in here. Let's try to recompile this entire thing. And what do we got? What do we got? Let me see. So that expected type pointer, but got i64. That's very interesting. Oh, this is because the final type was all right. All right. So basically, by doing that, we're allowing to mishmash between them or something, right? All right, this one is complicated. How can we allow this thing? I just want to be able to just sum them up. Maybe we can allow that for now. So essentially, if you try to sum up types, no matter what you get, is gonna be, yeah, it's gonna be whatever you have. We can also have the following thing. We can check that LHS and RHS have the same types, right? For instance, if compiled LHS type not equal to compiled RHS type, we can throw yet another error in here. So we didn't establish like a good conventions for binary operators yet, so that's why it's a little bit clunky in here. So let's put it this way. LHS has type S but RHS has type this. Okay, so we have this thing. So, and we also have binary OP. Is only supported. LHS of this. LHS has type this. Okay, and we can do something like compiled LHS type, and this one is going to be compiled RHS type. There we go. So do we have anything else? Okay. Compiled RHS. Is it working? Is it working? All right, so if I try to run it. Okay, LHS of plus has type i64, but RHS was type pointer. And if I try to do something like this, well, this is not the correct thing, but one of the things we can do in here is type check that this thing will work, right? Actually 1 + 1. Yeah, it still works. It actually passed the compilation. Okay. So maybe now we want to introduce some sort of a cast, right? So we have this, then you can do cast pointer 1 to this thing, right? And that way, yeah, you will be able to just take a pointer and sum it up. All right, so let me try to quickly implement that function. So load PTR. Along with load PTR and store PTR, we're going to have something like cast, right? So it's going to be else if sv equal fun call name is equal to cast, right? And in here we expect arity to be 2, so that means we're only going to have 2 arguments in here. So the first argument is going to be the type, right? So here's the type, and the second one is going to be some sort of a value, right? Oh, and this one is going to be actually rather hard. So we compile the argument 2. So here is the value that we're trying to cast, right? And maybe we're gonna have like different combinations and stuff like that. So for now, we only need to be able to cast i64 to pointer. So maybe that's precisely what we're gonna do. If value type is equal to bang type i64 and type is equal bang type pointer, what essentially we are doing, we are just setting result. We have to set the result to the type. Okay, so let's negate this entire thing. If this is not equal to that, or type is not equal to that, we have to throw an error. Right. Value is not equal to i64 or type is not equal to pointer. We're gonna say something like std error bang log fmt. We can't convert s to s, value of type s to s. There we go. So we're gonna allow only one single kind of conversion. Like in the future, we're gonna have some sort of like tables or whatever. So what we're gonna have in here? So does it have an original expression? Maybe it does. So that way I should be able to do bang log expression, bang log arg. And maybe I'm gonna put it on a fang call log. I think that would make sense. And bang type name value type, right? And then bang type name type. Okay, so we can only convert one stuff. All right, so let's try to test this entire thing. We're testing, and if I try to debuzz it, expected type pointer, but got i64. Oh, I see. So that means now in the binary OP, something like LHS, RHS, yeah, there we go. The plus should end up to be one of the things in here. So compiled LHS type, and also we assert a pretty important thing. We assert that LHS is equal to compiled RHS. So it's kind of important, because as we move things around up there, this invariant can change, and I want to be warned about that. All right, so now we're returning the same thing in here. Okay, let me try to do that, and it compiled. Okay, that's pretty cool. This entire thing actually compiled. So you can have pointer arithmetic like that. In the future, it's going to be a little bit easier. But for now, it's okay, I suppose. It is okay, I suppose. Maybe we didn't have to introduce the cast. Maybe if you have I64 and another one is a pointer, the final result is always going to be a pointer. I don't know. But I guess like it's a little bit more like stronger. It's a stronger typing. All right, so we can load the pointer. Now we can do arithmetics and stuff like that. And I wonder what kind of interesting stuff we can do with these things. For instance, can I do the following thing? Right, so I'm gonna start I with 0, and while I is less than, let's say, 10, what I'm going to be doing in here, I'm going to be storing 1, 2, 3, 4, store ptr I60. Yeah, I want to actually do U8. We need to introduce another type in here. Okay, so let's do the following thing. So it's going to be U8. Can we quickly introduce another type, I wonder? So before we introduce, I think I'm gonna compile this stuff. 428, implement cast and pointer arithmetics. Right, and let's push that right into the repo. I wonder how much work it will be to introduce type U8. That'll be rather interesting. Okay, so let's go to the parser. Parser.h. So I'm gonna straight up just do U8, and we'll see how it goes. Yep. In how many places we're gonna fail? All right. So here's the first one. U8, this one is going to be U8. Now we have 5 types. Next one. All right, so that's precisely what I'm talking about. Compile variable read. If you're trying to read bang type U8, what essentially we're doing, we're pretty much doing the same thing. We're pushing the address of the variable, but we're reading 8u, right? And that's precisely why I want you to have this switch case in here, right? If I didn't spend time adding this switch case in here, I wouldn't be ever warned about that, and I would end up troubleshooting like this stuff for ages. That was very important. All right, another one. So here we have the following situation. So this is a store PTR. All right, so basically here we have, I don't know why I could paste it like that, but yeah. So maybe we should have some sort of like a table between the types and what kind of instructions they have to use to like read and write things. So I'm not quite sure. And this one, yeah, there's a little bit of a duplicate in terms of reading and writing, so maybe we can extract that to separate variables at some point. Yeah, there's definitely something copy pasting here. U8, and the instruction is going to be basically 8u, hopefully. Okay. Variable assignment. All right. Case bank type U8. Yeah. So we'll probably have to extract all of that to something, but not for now. All right. right, so bank size of type. All right, this one is interesting. Finally, we have a different size, bank type U8. And this one is going to be 1 actually. Yeah, it's 1. Yeah, had a hard time to wrap my head around it. Okay, and if I got a break in here, thank you very much. Is it gonna work now? Let's find out. All right, my god, can I now go to like ptr bang, straight up remove everything and just define a single variable of u8? What's gonna happen? So like this. All right, as you can see, it got defined properly. Look at that. Yeah, there you go. Here's a variable, like a single variable 0 allocated in here. It's quite cool. Okay, so we need something like I64, right? So of course this entire thing takes a little bit more memory. Also we need to define heap base at the pointer, right? So now we have a heap base in here. And what I want you to do in here, I want you to start iterating. While I is less than 10, we're going to be doing the following thing. I equal I plus 1. Is it going to work? If I got a semicolon somewhere here, there we go. So it did in fact work. It generated all of that stuff. Beautiful. So, and what I want to do in here is, in fact, I want to store ptr. Oh, this one is interesting. So the pointer is going to be u8 heap base. So I'm taking the heap base and I reinterpret that as a pointer to u8. And what I'm going to be storing in there, I'm going to be storing I plus, I suppose plus 32, right? Or maybe plus the code of A. What's the code of A? ASCII. Right, code of A. Let me find it. It could be actually, oh man, 65, right? It has to be 65. And this is not going to compile, right? It is not going to compile because, yeah, expected U8 but got I64. Can I cast this entire thing to U8 now? I cannot, because cannot convert value of type I64 to U8. Right, so this one is interesting. So maybe we're gonna hard code yet another conversion just specifically for this example, right? Let me quickly see if I can do that. So where is the cast? Where is my cast? And I think it would be actually kind of better if we do something like this. Okay, so this is going to be else branch, all right? This is going to be else branch. And if this thing is equal to that and this thing is equal to that, we're going to just do that, right? We just allow that to happen. So we can simply reinterpret that value. So now I want to be able to convert value type bank type I64, right, I think, to the type bank type U8. Right. Do I need to truncate anything? I actually don't know. I actually don't think I need to truncate anything because it's going to be automatically truncated as I do the write. But it's not going to be truncated if I do any arithmetic operations, so we can come up with a very interesting and defined behavior here. All right, so I'm going to leave it as it is for now, just to get things going yet again. Okay, so if I try to compile this entire thing, it got compiled, believe it or not, it got compiled into something. All right, and after that, I want to have a special function, so to speak. I want to be able to do something like write ptr, right? So then I can provide heap base and the size. And what this thing will do, it will sort of like write a string, but with the provided size. Right, I know the size of this entire thing, and I know where it all starts. And also, by the way, I need to offset the heap all the time. Yeah, that's quite important. So here's a store PTR. Okay, so I'm saving this stuff, and I also have to do something like cast PTR to I. Right, I'm constantly adding I to the heap base, and this is how I store all of that. All right, is it gonna compile? It probably. We'll see. We'll see. Yeah, unknown function write PTR. Let's actually implement it super quick. Let's actually implement it. I think we have everything to implement this stuff. Else if sv equal fun call name sv write ptr. Right. So in the function we accept two arguments. Right, we accept two arguments. To be fair, I don't remember native write. Native write, what does it accept? I think it first accepts the pointer and then the size. So the order of arguments is correct. So compiled expression buffer, compile bang expression into bosom, bang bosom arg 0. There we go. And then we can type check expression. So this is the buffer, and we expect it to be of the type pointer. Right, we expect it to be of the type pointer. Then we need to compile size. Right, so this one is going to replace buffer size, and the size is expected to be I64. Right, there we go. So we've got that. And after we compile both of these things, we want to do something like bosom push instruction, bosom instruction native, and it doesn't accept any of the arguments in here, and the final result has the type void. Right, it doesn't return anything. Right, so we now got the buffer, which is the pointer, we got the size, and now we do the write. And if I remember correctly, write is implemented like this. So first you put the buffer and then the length, and yes, that's actually perfect. Let me see what we got. So if I try to compile this entire thing, okay, so there's some problems in here. Yes, arg1. That's why warning about unused variables is important, because you can get the situation like that. That's why it's important. Okay, it compiled into something. It in fact compiled into something that is very, very cool. Yeah, so here is the bytes of the counter, and here is the bytes of the heap base. And yeah, here's the code. I wonder if it's gonna work. Everything managed to compile properly, more or less. So, and there's a lot of reads and writes and stuff like that, so I'm actually kind of scared to even try to run this program. So, in theory, this program should just write something like A, B, C, D, E, F, G, and like 10 times, 10 first letters of the English alphabet. It's not gonna write the new line, right? It's not gonna write the new line, but we can make it write the new line. So this one is gonna be the new line. Yeah, something like this. New line. What the hell is going on? I don't know what the hell is going on. So, and this one is gonna be plus 10, right? And the new line that we put in here is gonna be, what's the new line? Is it 10 or 32? It could be 10 actually. Where's ASCII? Yeah, so it's gonna be 10. There we go. Might as well do something like this. Yeah. So we take heap base plus 10, but it has to be cast to the pointer, right? So this is the pointer arithmetic. And then we store it as U8, and we just save this stuff in here. And I wonder if it's gonna work. And also we actually have 11 characters now because we provided the new line in here. So I don't even know. So it would be kind of cool to also have some sort of like a count in here. Unfortunately, we can't have compile time constants, right? We can't have them, but we can do something like this. where we could just do something like that. Yeah, well, we definitely will need to introduce compile time constants. Like, I don't know if this entire example even works or not, and I'm really scared to even try it. I'm just super scared to try it. So because if it doesn't work, I have no idea how I'm going to troubleshoot it. So yeah, let's cross the fingers and let's just try fucking run it. Fuck yeah, God cooler, holy fucking shit! I first tried this for the flipper. Yes. Oh my god. So essentially, like in a nutshell, what this program does, right? It figures out, with the help of a compiler, where all of the variables end, and it uses the memory after the variables as basically as a heap, right? It just keeps piling things on top of the heap, right? And using pointer arithmetic and access, like read and write access to the memory, it just fills it up with letters A, B, C, D, E, F, G, H. So we don't really have a compile time values, but we can introduce a variable like this, and we can initialize it to 10, and we can just use this variable throughout the program, right? So this is going to be the count, and in here we're going to use the count, but here we're going to be using count plus 1. There we go. So that way we have a centralized place where we store the amount of characters that we're generating. And let's go. I'm going to go to the compilation, and there we go, A, B, C, D, E, F, G. But if I say that I wanted 20 of these characters, now we have 20. So yeah, fucking works. 26. There we go, 26 characters. That's pretty goddamn pogue, not gonna lie. So furthermore, we have a code generator that can generate native assembly from our bytecode. And in theory, this should work. Let's actually try to compile it down to the assembly. Right, I'm gonna go to build, tool chain. So bang. What kind of things we have in here? So we need NASM Linux x86-64. All right, so this is going to be the thing that we're going to be using, and we're going to use example ptr bang and segmentation fault. It in fact segfaulted. I remember we had something for that. Is it in the same place though? We have an issue for that. This is not how it works. We'll definitely need to fix that. And it was not added by me though. It was not added by me. And I think it is precisely in this place. Global scope bindings. Can I quickly fix that, by the way? CSV x86-64. So here is the thing, and it's 44. Okay, precompute label locations. So that means precompute label locations. Okay, so if you have label locations, you want to use them, right? So what if you don't have anything in there? So here could be a pretty easy fix. If bosom global scope is available, only then do that. Otherwise, return absolutely zeroed out label locations array, right? And in that case, it will not generate any of the labels. So that's a pretty easy and quick fix. Not the prettiest one, but I mean, there's no pretty code in production. There's only working code. All right. So now I can try to do no build test, and let's see how it goes. So because not everyone sets the global scope, and this is why I wanted to separate bosom from code generation, because yeah, stuff like that may happen. Okay, so we managed to generate the assembly for pointer example. Here is the native assembly for the pointer example. Okay, it's not even that bad. It's like almost 500 lines of code, and it's just really small. And it's only 46 instructions. I mean, 46 BM instructions, though. Not bad at all. All right, so let's actually try to compile this entire thing. It's going to be nasm o ptr o ptr asm, and we got object file, and then we want to link this entire thing into ptr example, and I think file format not recognized. Huh? Why did you not recognize the file format? Com executable. What did I use to compile nasm? Yeah, f-elf64. There we go. And this one is elf executable now. LDO-PTR, PTRO, and if I try to run this, by the way, native executable, x86-64 executable, right, so it should print the English alphabet, and it's a native code that got generated from this non-existing programming language, right? So it's a little bit clunky, it's a little bit rough around the edges, right? So you have to do these casts, and we don't have a syntax for pointers and pointer arithmetics. The pointers are only void star, but they are working. It is working pointer system that we can now try to improve upon, right? We can try to improve upon this thing. So one of the things we want to do, maybe we want to have a better syntax for reference and dereferencing the pointers, like instead of store PTR and load PTR, we want to have something that is ergonomic and easy to use. I would like to have that. Also, I want the pointer to be a generic type, so I don't have to pass this kind of stuff around, so I can just say that. Well, yeah, we also need to retain pointer without the type, because sometimes you don't know what kind of stuff you want here. So, but maybe we might allow like heap base to be set to pointer of any kind, but it must be pointer. You know what I'm talking about? It must be pointer, but it could be any kind. So, and that way it could be greatly simplified. So, all right, so let me do a committee. All right, so let's actually commit these things separately. Quick and dirty fix for 30. Okay, and this one is going to be something like, all right. So we introduced U8 and some other stuff. Did we also introduce write PTR here? All right. Implement enough functionality to generate English alphabet. Right, so there we go. So what kind of to-dos we have? There's no generic pointer type. This is the first thing I want to have. And another thing I want to have is a special syntax for pointer, for reference and dereferencing the pointers instead of these clunky functions. So store PTR, write PTR and stuff like that. Okay, so I'm gonna put it to do in here. There is no special syntax for actually dereferencing the pointers, because referencing, I kind of like the idea of just using PTRX. I kind of like it, but for dereferencing, it's just like it would be better to have something else, or I don't know. Maybe it could be just a function unref that accepts this kind of thing, and so you would be able to actually put it into the left-hand side and assign things like that. So yeah. That's kind of interesting. So yeah, so you can have something like pointer x, and then you can do deref pointer and just assign something to it, right? That's not a bad syntax. So, but we need this needs a special special treatment because we have variable assignments, and variable assignments can only accept names at the left hand side, so you cannot accept like expressions in here. So I don't know what we can do in here. We'll see. Okay, so this is another to do that we'll need. Okay, 428 additional to do about the ref syntax. And I guess that is it for today. So it was a 2.5 hour session, and I think it was worth it. So the result of the session is this working code. It's not the practice code, but it is working for now. So, and then now we can try to improve this code, right? If I was trying to improve it first, I wouldn't get anywhere because you can't improve something that doesn't exist. We have something ugly, but it does exist. So now we can improve upon it. All right, that's it for today. Thanks everyone who's watching me right now. I really appreciate it. Have a good one, and I see you all tomorrow. Tomorrow we're going to continue working on these things, and we're going to continue improving it and making it better. And yeah, check all of the links in the description, and I see you all tomorrow. Love you all.